Like,
Oh, yeah, yeah.
I googled like for what it is for a barn item and I checked the matches.
Okay, so okay, good. How much was it?
I got 1.16 times 10 to the minus 11%. But of course, that's not what it really.
That's the classic.
Imagine.
Reactions.
You haven't graded the homework 9 yet, right?
No, there's one homework I have missed on 11 and 9 this week.
I noticed you skipped over it, so I was wondering if it.
Yeah, that was what the guardian was also asking. It's just I'm hoping that I can read it properly.
Yeah,
I think
I'm
as it
no
gets-
rush, no rush.
Yeah, as it gets farther, it will be harder for me to grade in a very, how do you say, in a picky manner, because most probably you guys will make conceptual errors. Will be more lenient on the later homework. So try to submit even if it is not complete and all that. But until 9, I'm hoping that I can be picky. I can demand that. That post homework 13. This is the first time I'm going until homework 14 in this course. Total homework.
I think last year was 9 works.
Typically 10, yeah, 10 homework.
Well, some of them are short.
Yeah. So that's what I. Usually I cannot do it this speed.
Let's set it will be late 5 minutes.
Oh, yeah, that's correct. Today they have meeting. Yeah, I can do the logistics.
I accidentally left my notebook at home. Is it okay if I just take pictures with my phone?
Yeah. Oh, this is the.
Watch.
Well, I know.
Yeah,
I like to have it.
sure. Yeah. I think I don't mind.
Next week, Tuesday, we have potluck at the exact time of the class.
Yeah, I noticed.
Postpone it,
So what do we do?
postpone the class or change the time of the class before or after the potluck.
But are you guys available? I wouldn't be surprised if
There's
you.
a pot.
No, you're invited, by the way.
I am.
Yeah, so I have the authority to invite, so I can invite you. You're invited now.
What is it for?
It is between 11 o'clock and 1 o'clock and 2 o'clock, 11 o'clock to 2 o'clock.
11 to 2
And-
on Tuesday.
Do you know the Bucky's? Tent, Bucky's Dome, yeah.
Bucky's next Monday.
Oh, yeah.
Right next
Yeah, I
to the
know the dome,
engineering
yeah.
building.
I just forgot what it was called.
Yeah, I think it's technically or officially called the Bucky's Dome.
Yeah.
And it will be there if the weather is not good, then it will be on the second floor.
Second floor, right?
Necklace.
So 11 to 2 on Tuesday.
Yeah.
I'm assuming the potluck, which means I should probably bring a dish, right?
That'll be great, but it's not necessary. Don't feel obliged.
I
So
could bring something.
I have
could bring
come-
something Persian.
Yeah.
Or even.
We are a small department. It has happened that very few of us there bring food and it's not sufficient, but
How many people?
often it's a lot of food.
How many people are in?
We are about, I think, how many? 25 people?
Already about 20.
Yeah, feel
We
free
can
to bring.
have our class over there.
Oh, yeah.
Yeah.
In teach class.
Yeah.
Bring a projector.
Is that what you guys want? Yeah. Okay, so surely we won't have class at 12:30. But can you guys give me an hour somewhere here or there?
Or before the class.
Or,
after
okay,
the
how about
class.
this? I'll make it homework. Okay, so the topic will be covered in the homework. So, okay, so next, yeah, good point. Yeah.
So. Wait,
I can make you guys listen to a lecture, right? One of the old lectures I just asked you to do.
If everyone is available, we can do it after the class or before.
Are you guys available? That's good.
I'm
I
available.
am.
At 2 o'clock?
I'm usually available.
Are you guys available at 2 o'clock on Tuesday today? Are you free?
Sorry.
Are you guys free at 2 o'clock today? Or it's not that, okay, so the proposal is that, sorry, so the offer is, proposal is that next week from 11 o'clock to 2 o'clock, that is the department potluck. Are you guys aware of that? That's, and it's good for us to be there instead of, being in the class. But then the request is that can I have that lectures just so that if it's not, I will think of something else. So that either the class is cancelled or we can have, so the question is that are you guys available at 2 o'clock? Can you? Is meet at 2?
So, the labs, is the last week for labs. I have office hours at 2:15. I'm not sure whether it will be next week or not. If I don't have to take office hours, then I'm free.
No, officers, no sacrifice.
No, so the lab is already, this is last week for labs, right? PA labs. So I think, do we need to carry?
I don't know, don't ask me. Because officially I cannot ask you to cancel an office hour. Office hours comes before, so that's a commitment you have. You can skip it, I cannot ask you to skip it. You see my point? So
So we have to carry it up till last
I
week.
really don't know, honestly. Yeah. Like surely in the exam week, there is no office hours, that I know. But last week, is there an exam for the course?
No.
A lab exam?
No.
Is, when are they due? When is the submission of the lab reports?
It's during class.
Oh, yeah, that will be next Wednesday.
Yeah, so they can come and ask
Yeah.
questions, so you have to hold the office hours even after. So. Okay. But now let's cancel. Okay, reasonable? Unpopular request. It's canceling, I'm not canceling it, but
Cancel the class or what like?
funny. Nice humor though. Let's cancel the class instead of. Okay. Good one. Okay. Okay, so, first the cancel of the class. I can almost cancel the.
No, I mean, me going there,
Huh?
not the whole part like,
Oh, I almost thought you wanted to.
no, no.
Okay, so, yeah, so. Let's. Yeah. New class. On May. Second Tuesday. So 2 o'clock is again another kilo, 4 o'clock.
Yeah.
It won't work. I know from experience that it doesn't work. Okay. I'll make your homework.
Is it the same class as last year? So we can go.
I don't know. I'll have to look into it. Yeah, probably yes. But I'm not sure.
It's gonna be the routine homework.
No, I will, the homework will be there. That's all I'm trying to say.
Oh,
We have
Like
to
in
watch the
homework,
video.
it's just that class helps you with the homework, like I build things. Here I will directly put you some equations or something like
so
that.
the homework is optional, or we have to submit, like last year, we got some optional stuff.
Oh, really? No, this one I will have it because it is scattering. Yeah, submit it, but as much as you can. How about that? Like that's what I was telling before that we will make it. I have not graded homework 9 primarily because I want to be picky in that. I'll try to be picky at least. If you guys did very good, I cannot be picky. But after that, I'll stop trying to be picky. It's more going to be on participation. So if you do all the steps, that's good enough.
After homework 9. Or 30.
Start off. How 12 after 12. Okay, after today's homework, so it gets a little more harder, but that doesn't mean that you don't have to do it. It's just that I will be less picky, but I look for. Usually what I do is I overall look at the whole class. After every one of you submitted, if all of you have done reasonable and I don't have any reason to categorize you guys, so I just give full points. But if I find something very basic that is wrong, then I take off. Is that clear?
Yeah.
So, okay, for now, no class. That's, I think, a good suggestion, but I would have liked to have the class too. I think.
I can't like that.
Yeah, but we're a small department and this point is correct.
You can record one.
Yeah, can one of you guys come and sit? I would like someone to talk to instead of recording at home. I've noticed that whenever I record, like I promised I'll make solutions for the undergraduate physics. And I think something stops me. I start at 6 o'clock somewhere in the evening. Okay, I have to do recording. And then I procrastinate. I keep delaying. I'll do everything else but that. And then eventually at 3 o'clock, 4 o'clock, I'm recording it. And I think I hate recording, I guess, because you talk to yourself. I don't know what it is, but something I don't like about it. So yeah, I will be glad to record, but one of you guys has one of you guys could volunteer and just be a dummy there. And
Can you make it like a Zoom class? And record the Zoom?
yeah, so when can we have it? Are you guys available in the evenings, late evenings? Can we have a class at 9 o'clock, 11 o'clock? You wanna have it for a change? What?
I think.
Huh?
We are all available at that time.
Yeah, so shall we try this? Mavs, you might be the
9 at on Tuesday.
any day.
Sure.
Shall we try that? All right, okay. When is 9 o'clock a suitable time to begin with? Pravina? Rishi? Atul?
Fine.
Mavs?
Yeah.
Right, so yeah, let's do this for a change. Yeah, that's kind of cool, I think. Have a class at 9 o'clock.
Maybe in our pajamas.
Your call. It'll be recorded. If it becomes popular,
Turn the video off.
it'll become viral.
We do Zoom, right?
Yes, and that's the only thing I request whenever it's on Zoom, try to put the video on. It helps again. I won't ask you guys in the sense it's not a requirement, but it just gives a more friendly environment. Like the difference between classroom and there is that you really don't know what's that behind.
Can we have custom backgrounds? One time I played the whole B movie in the back.
What?
The B movie,
What's the B movie?
it's a very like, very mean movie about a bee.
About a bee.
What the B movie?
That's the guy from Seinfeld and so.
Like youngsters really do this, right? They keep a background of themselves and they're not there actually.
Oh yeah, they made like joke videos that were like some of like someone coming to like strangle them or like kidnap them or something.
Or a screen saying connecting ...
Yeah. Like I teach my nephew who's in ninth grade, and he does all these pranks with me. He does for fun. He enjoys. Okay. So we have no class and Tuesday is good enough?
Yeah.
Right, so Tuesday, great, so I like. Maybe next semester we'll have always a night. But I think this gives me the idea that whenever I cancel a class, I can have it at 9 o'clock, because I used to never get a suitable time. Now I know. So, okay, so there is, so class at 9 PM. May 2nd. Tuesday. Zoom, right, from Zoom. Same, this one. But same,
Will you email us the link? Or,
this is the same link. Oh,
You don't have the link.
yeah, we don't have the link because you were.
you don't have that link. Yeah, it's somewhere on my webpage.
Oh, okay.
I can email.
If it's in the syllabus, there's.
Is it on the syllabus? Probably, yeah. Yeah, okay, otherwise I'll send it to you guys. So, yeah, somewhere, there on my page. Okay, good. Save the class. Okay, so that's almost half an hour. Homework 13. May 2nd. Tuesday. Homework 14. Is going to be due May what? Friday. It will be officially due at midnight, but this has a buffer in the sense that you can submit it on Monday or fine, but officially it is due on Friday. So, but you can take, I'll be lenient about.
What do you mean by midnight?
I didn't mean,
Well, no, you said by midnight.
yeah, I said by midnight, yeah, what do I mean by midnight?
If we,
Yeah,
Aren't
you
the
cannot
opposites,
submit
but-
it because this is not D2L, right? I usually say this for my undergraduate class because they
Ah.
submit on D2L. So here that's at 4:30, officially due at 4:30, but that's just an official statement. So
So you will be here.
you don't need me, right? You can submit it in
Your mailbox.
the mailbox. Always it's due at the mailbox, like you can submit it to me if you want.
so the buffer just means like, we,
It means it's not
Yeah.
strict, not strict, it's not. Right,
in case, like,
yeah, Monday. Or. Final exam?
Midterm two.
Oh, yeah, there's a midterm too, what
let's
happened?
do
to-
May 1st.
Yeah, midterm too, let's do that. It's, you know, this course is piling up at the end. I couldn't believe it.
As your most.
Has to more, I try not to.
Because they realize you're running out of time.
But again, if you're taking more courses, concentrate on other courses. Do it just for yourself, right? Don't do it for grades. Don't panic for the grades. That's my suggestion. Okay. Final exam. I'm still thinking on the final exam, so nothing concrete yet. But it's going to be mostly take home with that problem also in the first. And there are evaluations, so complete the evaluation on D2L. That would be,
The midterm is due on May 1st, not April 30th. Because we said, because April 30th was a Sunday.
that's. Evaluations, there will be two evaluations for the course. One is university has an evaluation which is on D2L. Which formats, the format is mostly very universal, which is applicable for every course in the university. So I encourage you guys to do that. I do read the evaluations, so it helps. It may not help you guys, but for the overall, I think next batch or so, I think it helps. So if you feel obligated, or what do you say? If you feel that you should contribute to such an activity, you should take the evaluation. So I'll encourage, I do read it, I do try to incorporate the suggestions, so I'll encourage it. There will be another evaluation from the department, which will be done in the classroom, probably not, I think most of you guys are PS, so you guys have also done it for the same thing. I will also be doing, again, I do read it seriously and I will try to accommodate it in the next semester also, so you guys don't get it. But in the long run, I think it's a good activity to have. So, okay, so that's just. Okay, so we are doing radiation. And mostly what we want to talk about is that there are some sources, charges basically, which are described by R prime, sources there, and you want to observe it somewhere very far away. And in the radiation zone, which is described by R prime very much less than R, this is called the radiation zone. And we have been able to talk about what's the power radiated per unit time. Oh, sorry, energy radiated per unit time per unit solid angle, right? So that's what we have been able to calculate. But often we talk about most of the devices, the sensors that we use, they are color dependent, right? Red light has a certain or some sensors are sensitive to red, sometimes are red to green. And if you're using radio waves, they are usually dependent on the frequency very much. So we would like to know the same idea that we did before. We would like to find out what is the radiation dependence, what is the frequency dependence of this radiation that we're talking about. And frequency and time are related by Fourier transformation. Right. So if you Fourier transform our solution, you can get the frequency dependence, but we will go back to the very first step, starting the Maxwell's equation, and redo the whole radiation problem in the frequency space. Okay, so the complete thing. So it's sort of a review at this point, and we go back all the way, and it has advantages. It's much easier to do that than do the final solution and take the inverse, because then because there were so many approximations involved, sometimes it is safer also to do that. Okay, so what was our idea? Magnetic field was equal to del cross A, and electric field was gradient of phi of the vector potential, scalar and vector potential. They satisfy the equations. They satisfy the wave equation or inhomogeneous wave equation. Phi of T is equal to 1 over epsilon naught. So give me the charge density as a function of time. This equation tells you the scalar potential as a function of time, and it's the same equation for the vector potential also. We put mu naught times J or T. Right, is that clear? So this means that either it can be this or this, correct? So that's your wave inhomogeneous wave equation, and whenever there is an inhomogeneous differential equation or partial differential equation, you use the Green's function. So Green's function was minus square. So you consider a point charge. Yes. Prime, and that's equal. And we had the Green's function as if it was a a point charge, and if it was statics, it is 4 pi r minus r prime. And how does it change for time dependence?
Delta function.
Delta function, right? Instead of 1, this is a scalar potential for point charge. That is a delta function, so it is t minus t prime minus r minus r prime over c. That's a change in dynamics, right? That's the only change in dynamics. If you can incorporate this completely, you're in that solution. In a sense, and phi is related to phi is related to rho in terms of this Green's function. So let me write that down.
So the first equation is homogeneous, the second one is inhomogeneous.
No, because both are inhomogeneous, right? What do you mean? Ask me again.
The homogeneous and inhomogeneous.
No, homogeneous is whenever you have, for example, second derivative of x squared plus first derivative with respect to x. So let's say a of x plus b of x plus c of x. If this is 0, that's homogeneous. If this is not 0, that's inhomogeneous. And that should be an F also. So the operator on something. So if it's not 0, so this is inhomogeneous. This is a very special inhomogeneity in that sense that it contributes at only 1 point. So the main idea is that this inhomogeneity can be broken into point by point. There are lots of points that is contributing to that. Let me get the solution for 1 point and then I will just integrate it. So that's superposition principle. Get me the electric potential due to point charge and then just add it up. Right? That gives me if they are linear. If it's a linear solution in the sense that if the physics allows superposition principles, then that's a scenario.
So Green's function is everybody's homogeneous except 1 point.
Except 1 point, exactly. And that's the idea that, so you say that it's only 1 point, so I'll delete it. So it's basically you solve the homogeneous equation. And at that point, you patch it. So think of a one-dimensional situation. On the left side, you have a homogeneous equation. It is solvable. Right side, there is a homogeneous equation, solvable. And the boundary, you patch it. That's the boundary conditions, which is dictated by the equation itself. By the Green's function itself dictates it, and you patch it. And you deal with that. I have not emphasized that very much in this semester, but somewhere else, like in math methods, you do a lot of those equations where you patch things up. That's the idea of the Green's function. Okay. Okay, so yeah, so at least formally speaking, it is phi of RT. Once I know the Green's function, it's always so this is d cube r prime g of r minus r prime t minus t prime and rho of r prime t prime, right? So that's your. Once you know the solution, then that's what it is, and then epsilon naught. So that's the idea of Green's function, that if you can solve for it, then it's a matter of doing an integration. And yeah, so it's and what's missing in this? Let's take it that. I forgot a t prime integral, right? So this is a t prime integral. And t prime is not on a volume, it's a one-dimensional. Okay, so I can put the limits. This is on all space. Basically, r prime is a coordinate, you scan it. In words, if you have to say it, pick every point in space and ask, oh, is there a charge on there? If there is a charge, how much does it contribute? That's the basic idea. Okay, so yeah, so this will be equal to 1 over 4 pi epsilon naught. If I make the substitution, d cube r prime, dt prime, the limits are undistributed. And let me write this as rho of R prime. T prime. R minus R prime. Delta portion of T. It's T prime. Good. That's just a formal expression, so that's what we're doing. We rearranged Maxwell's equation, derived this wave equation, inhomogeneous wave equation. And in terms of that, we can get the scalar potential. Vector potential is pretty much identical. We replace rho with J, right? And epsilon naught with 1 over, that's idea is the same. But we want to do frequency dependence. Frequency dependence is Fourier, you do this by Fourier transform. Let's take any function satisfies this, but let's take phi itself. I'm going to use the same phi. Remember your Fourier transformation. Notice I'm transforming only the time. In general, this should be written as a tilde. It's a new function that's equal to et e raised to I omega t times t. And this is minus infinity to plus infinity. That's a Fourier transform. And if I want the inverse Fourier transform, this is equal to add up all the frequencies, e omega over 2 pi minus omega t by tilde of R omega. Okay. Or we will get lazy, or I will get lazy and stop calling this tilde. More than laziness, it avoids clutter. Right? So it is understood that whenever it's a function of omega, I'm in the Fourier space. Okay. What's the dimension of potential? Potential here, pi. What are the dimensions? Potential Q over R 4
1
pi.
over R. 1 over R.
No. Potential is Q over R 1 over 4 pi epsilon naught, right? For a point charge. The dimension of that. Why do you say 1 over R? Then what about epsilon naught?
Dimension is volt.
Volt, right? So volt is, let's say, joules over charge, right? Like 5 times Q is energy. So this is in joules. So if I'm interested in units, that's joules per coulombs, right? Just units, let's say, instead of dimensions. What is the dimension of phi of R omega? The frequency space.
You have to multiply by T.
Correct, right? So always remember that just because something has a unit that we are used to, in frequency space, it changes. Its dimensions is different. Okay, so current and frequency space gets multiplied by time. So what's the dimension of pi in the frequency space? It's a time. This time shows up. And I have to multiply this time exponential. What's the unit of exponential? The dimension of exponential? Doesn't have any dimension. It's always a number. So this is the dimension times t. The other way, if I want to get the dimension of this is 1 over time times this. So you should always remember this, because we will be writing equations, and always when you're doing a dimensional check, I want to keep this in mind. Remember, these are different functions, but I have removed that dependent. Okay. So I'm interested in the frequency dependence of the electric potential. So I have to just substitute this in there. That's all, right? So let's do that. So phi of R omega. So the frequency dependent scalar potential is already an integral in time prime, t prime, r prime, and now I do a t also. Okay, so this is let me do it here. So I have 1 over 4 pi epsilon naught E cube r prime, dt prime. And so, and I can actually, so let me do the E here. Rho of r prime, r minus r prime. Oh, exponential also, right? Exponential minus I omega t, function t minus prime. And this is, let me begin by doing the integral on time, the observation time. So I'm frequency is like you add up all your times. You have to go from minus infinity to plus infinity. So it's an average in a sense with the exponential as its as its amplitude for each frequency. This is a straightforward integral because it's a delta function. Integral of a delta function just means that replace the argument with the appropriate whenever it goes to 0. So here it is straightforward. T has to be replaced with T prime and this quantity. So T shows up only here. That's the only place where T shows up. I will replace that. So let me do that. 1 over 4 pi epsilon naught d cube r prime dt prime minus infinity to plus infinity. This is prime as rho of r prime t prime over, and now I have exponential. Oh, mistake. This is plus, right? So this is plus. Plus. It is plus I omega. I get replaced with T prime. And I also get replaced with I omega over C r minus r prime. I'm just going to rewrite this as just rearranging, not even writing in a very different way. Simply rearranging this I omega over C r minus r prime over r minus r prime. That is, this only depends on r minus r prime. So I've collected everything that is r minus r prime on the left. And whatever is having a T prime dependence in it, I collect it to the end. That's e raised to I omega T prime rho of r prime T prime. What? Yeah, question?
What is the if like delta function becomes an exponential
No.
with the integral?
Oh, here. Yeah, what delta function does is, see, I'm doing T integral.
Is there two time intervals now?
Yeah, there were
Yeah.
two time integral, right? There was already a time integral here,
Okay,
and this has a new time integral.
okay,
So I'm switching T to omega,
okay.
right? So clear?
Yeah.
What is this equal to? This integral equal to? It's the same thing, except instead of a scalar for potential, it's a charge density. It's the Fourier transform of the charge density. Charge density changes in time. We are saying, I'm not interested in the time dependence, give me the frequency dependence. So the frequency dependence of the charge density, how many colors there are in the chart, like each frequency oscillates, right? Like 5 hertz, 3 hertz, and so on. So you're breaking up those frequency. And suddenly, this Notice the frequency dependent scalar potential has with a frequency dependent Green's function if you want, and a charge density which is no more time dependent but a frequency dependent charge density. It is rho tilde in principle, right? New function, and in a sense. This seems to suggest that this actually, like the Green's function 1 over R. Right, that's your Green's function or a Green's function you do it for a Laplacian. Every function has a what is it? Has a Fourier transform. This is now T, right? The T minus R if you want. That's how the delta function is in dynamics. Correct. If I set T prime equal to 0, that's how it looks like. You can ask, what is the frequency dependence of this Green's function? Right. What's the Fourier transform of this Green's function, or the dynamical Green's function? And that's the Green's function. That's what this means. Okay. That you will see this again in your homework where I do this more clearly. You do this only from starting from this equation, do the Fourier transform, and you can do the same thing. But what this suggests is that scalar potential in the frequency space is given in terms of the charge density in the frequency space, or and that's the Green's function. Notice each mode separates, each color separates. So if the charge is oscillating, 3 Hertz completely works independent of the 5 Hertz. As far as the scalar potential goes, electric field of a red color and a blue color is completely independent. They just superpose. But energy is square of it. So there are interference terms. When you square any quantity, there are interference that happens. Right? So that's what is the idea. Like electric field is linear, but whenever we square things, there are superpositions that comes in. Right? This is for each frequency, it adds separately. For one frequency, there is a phi, another frequency, there is a phi, and phi of RT is sum of all of these quantities. Okay, that's a scalar potential, and similarly, you have the vector potential, right? So summary is that we have now this is equal to 1 over 4 pi epsilon naught d cube r prime exponential of I omega over c r minus r prime or prime omega, and vector potential is the same. Okay, that's your scalar and vector potential. Once you have that, you can get the electric and magnetic field. But remember, this is the total, right? We have not yet made the radiation approximation. Like radiation approximation has this feature that R is very much, observation point is very far compared to the source point. So that's mostly done by replacing R minus R prime with R minus R hat divided with R prime. If you make this replacement, and that's mostly how it captures most of the radiation terms in. Make this substitution in here. In the denominator, we saw earlier that you don't have to make both the substitution, one is sufficient. So phi R omega is equal to 1/4 pi epsilon naught cube R prime. So basically scan over for all the sources. I omega over C. This is R minus R hat divided with R prime. Remember, R hat is this direction. An origin, and that is a R hat, right? R hat is in this direction. And in the denominator, just keep an eye. There's no need for the second one because it's higher order, and that's rho of R prime and omega. We are in R prime integral, this comes out. So 1/4 pi epsilon naught. It can come out, R can come out. Or R.
What did you use for the denominator R minus?
This should be R minus R prime, but earlier we argued that even if I put the second one, I'll have to invert it, like 1/1 minus X is equal to 1 plus X. That's a second order, right? So this is 1/R, and the next one will be 1/R squared, because I've already, according to this. What I meant was 1/R minus R hat dotted with R prime is 1/R times 1 minus R hat dotted with R prime over R. That's equal to 1/R times 1 plus R hat dotted with R prime over R. So that's higher order, right? Plus order 1/R squared. Right, so it's not needed to keep that because it's more contrary, it's not a leading order. We did the same thing in the earlier also, so here I directly did that, okay, good. And we have E cube R prime exponential of minus I omega over C times R hat dotted with R prime and rho of R prime omega. We did the Fourier transform. What will this be? F of R comma omega will be equal. I can also Fourier transform in the position, right? This will be 2 pi whole cube e raised to I k dotted with R and f of k dotted with omega, right? And the same thing, f of k omega equal e cube R e raised to minus a k dotted with R of R omega. Is it clear? This is the Fourier transform in the position basis. I can Fourier transform in the time basis, that gives you frequency. This is the wavelength if you want, right? In the position basis. Clear till now? If that is the case, and if you observe this, this is nothing but the Fourier transform in the position basis of the charge density. Except I have to read this as some quantity, so that's a k if you want. So when I Fourier transform this R, I get a k dependence, right? Now the k dependence is omega over c times R hat. Remember your wavelength, right? Omega over c is equal to, what is that equal to? Frequency over speed of light. Lambda,
Where are you going?
is that correct?
Lambda nu.
Lambda nu.
One
K.
lambda.
1 over lambda, right? It's actually 2 pi over lambda. K, yeah, someone said K, right? So it's K. Perfect, very good, right? So this is nothing but omega over C r hat. So I'm going to start a notation now. The K that I'm going to write is not generally K, it is omega over C, the wave number. But I have a direction now. The vector, so the direction is r hat. R hat is here. So it's a wave going in that direction, if you want to imagine it like that. But it's k hat, that's a vector, right? Its magnitude is omega over c, direction is r hat. Observation point, right? So something is moving in that direction. So it's not, or you should ask, what is the vector k, right? So in this case, it is r hat, right? Usually with the monochromatic wave, it's direction of propagation. Okay, that's a notation, just a definition. And if I do that, so this whole thing now, if I use this phi, the scalar potential in the position basis, this position notice is equal to 1 over 4 pi epsilon naught e raised to omega over c times this is nothing but k dotted with r over r. And this is the Fourier transform K and omega. No integrations, nothing. Very straightforward. Right, when we were in the time domain, we had to do an integral to get this the expressions. Radiation is, if you Fourier transform your charge density, you're almost done, right? You might have heard whenever you're doing X-ray, you go into the reciprocal basis, right? The reciprocal basis of a crystal is what you see in an X-ray picture, right? Why is that? Because it is the frequency. Fourier transform is what radiation captures, right? So if you're in the Fourier space, you don't have to do anything. It's just to interpret that. Now you have to go back and see what is happening, right? If you want to interpret what is happening, because we are used to time. If we were used to, if our sensations were frequency dependent, we won't have to bother to go into the time space. But for our understanding, you have to take this into the time basis, and that's why you go from the picture that you have, which is in the reciprocal basis, into understanding what is going on for the time. Is that clear? What
So
is that? Yeah. Mhm.
first, we came from time to frequency, right?
Correct.
Then space toward case like various vector.
K is a wave vector, yes.
Yeah.
So we went from time to frequency, position to wave vector.
Yeah.
Okay, so here is the exercise. What is the dimension of K omega? Okay, quiz. What is the dimension of rho of K omega? Can you tell me, right away?
Same as the row, but there is R.
Joules time.
Tell, the look trying to confirm.
Yeah, joules, meters, second.
Meters are not just meters, there are 3 of them, right? Meter cube. Right, good, so not joules, it is rho, right? So this will be equal, so dimensionally speaking, because there is an integral over d cube r, dt, exponential, and a rho, right? So this is L cube time and the dimension of rho. Like the standard dimensions, which is basically charge per unit volume.
So when you say cancel out,
Yeah, they will cancel out. So it is just charge times time. Yeah.
So the integral of t is for the frequency to time, like going back.
Yeah, going back. Correct. So for example, if it was charge density, it is interesting, right? Charge density in the Fourier space, right? K omega is equal to, like Mass was trying to point out, so it will be L cube times time, then let's make it current, how about that? Right. Current. No, right, just the current, it'll be L cube and then charge over time, right? So the time cancels out, and that's, yeah, I was thinking L cube. I should have. Hey, but. Hey, put it down. So I think I can make the point for you guys, right? So, be careful with the dimensions. Okay. This is in the frequency space and the Fourier transform position space. This is what is often called the reciprocal basis of a crystal. And if you know the reciprocal basis of a crystal, it immediately tells you what your X-ray or radiated picture will look like where it will dominate. Okay, so you have scalar potential. So I have the vector potential also, right? It's almost straightforward. The same idea. So phi of r omega. Notice I'm still in the position space, but I have Fourier. It's a Fourier transform of the charge density that is contributing. E raised to I. Sometimes I write this is also the same as IKR, right? Okay, I've written it in three different forms. I omega C over R, then I K dot with the same idea. And then you have rho of K. Let me write this as omega over C R hat times omega. Like Fourier transform. A R omega is equal to mu naught over 4 pi. This is K. Okay. You have A and phi now. We are interested in let's say magnetic field. Is equal to del cross with A. Notice, and maybe I should say, oh, but now there is a challenge. Maybe this one was simple, but the electric field is not straightforward, right? P is defined as gradient of phi of P minus of P by dt A of RT. When you go from time to frequency, if there is no time derivative, then it's okay. But what is electric field in the frequency space? This will be simply go to frequency space, that's straightforward. But okay. Time dependent function And a frequency dependent function, how does the derivative go through? Notice that, let's go here. If you check out, if I were to take the time derivative of this function, where will it hit? It will hit only here. Time. There is no time in this. There's only one place it hits. And what it does is that it brings down a minus I omega. So for all purposes, if in the Fourier space, derivatives are replaced with frequency. Okay, if it is a gradient, it is replaced with IK. Okay, the Fourier transform variable. So this becomes minus I omega, so that's I omega. Is that clear? Point that. So for all purposes, time derivative becomes minus I omega, because that's what this is involved. And when you're taking a gradient, it hits here, right? That will be IK. So for our purposes, the gradient operator, if you are in the Fourier basis, this is I times K.
But it doesn't affect this one, this gradient.
Which one? I'm going to do that. I'm going to do that. But it is, one has to be a little more careful because phi is not just, yeah, I mean, yes, okay, that's what will happen. Yes. But one has to be a little more careful in the sense that there is an R, and other dependence. So it is an approximation that you're doing. So in that sense, maybe I should say, if it's a proper function, it is a true statement that gradient can be replaced with I times K hat. But since I'm working in the radiation approximation, one has to be a little more careful, but it turns out to be the same. So it works out exactly the same, but if you want to do higher orders, then you should be more careful.
What does it mean, proper function?
Let me do that. Let me show that. Instead of replacing, that's why I did not replace it. You will see that I have to do that. Yeah. Okay. Okay, so so this was clear, but what about the gradient of the phi of R comma, this was yes, right, phi of R omega, right? This is equal to gradient can act on any of these pieces, 1 over 4 pi epsilon naught times e raised to I k r over r, and then I have the rho a over omega. So in Europe, so as Arian pointed out, this is nothing but IK times 1 over 4 pi epsilon naught. Sorry, not 4 pi epsilon naught, the whole thing in the Fourier space. So notice what I'm going to, what am I saying? Yeah. Okay. Yeah. Okay. This is equal to phi of k omega. That's a true statement. But this is helpful only if I know phi of k omega. Only if I know the Fourier transform of this function, that is this, right? And Fourier transform of that requires more work. But instead, I say that I'm not interested in the full Fourier transform. I only need the radiation approximation. Give me the first term and I'm happy, right? So I won't do this. Instead, I'll actually operate it. Okay. So this is a true statement, which is what you were asking as to what is that function, for what is a good function. Any function, as far as you know this Fourier transform. I don't know that. So instead, I will say that I'm going to operate that. Was that a question, Ryan? You had a
So you just want to take the gradient acting on that E term. Makes it.
That's what turns out it to be, but then that will be. Yeah, exactly, that's what is going to happen, yeah, I'm going to show that, yeah.
Okay.
Good point. So there are three places where it can hit on R, right? One is this, and this also has an R, remember, right? K has omega C over R hat, right? K hat is omega C over R hat. So I can hit on any of the three. And remember, gradient of R is equal to R hat, right? That's R hat. So gradient of K would be equal to omega over C times R hat, which is K. Right. So whenever I'm hitting here, there is a omega, no, did I say that? KR, right? KR, right? Because omega over C is K, and then R, that's your R hat. Right, so that's your K. KR here gives you that feature. And so I can hit here, here, or here. When I hit this, this is 1 over R squared, higher order. Right? When I hit here, higher order. Right? That is what we did earlier, so I'm not going to go through that here. So it is only this piece I'm going to do. That is my leading order in the radiation approximation. Can I do that? Okay. I'm going to throw away these two terms, and I get, so I bring down an IK, and this time I'm doing more than this. This is equal to 4 pi epsilon naught times e raised to IKR over R times rho of K omega. This doesn't mean that this is equal to this. This is equal to this only in the leading order. Okay. There are more terms in there, but in the, for our radiation purposes, that is okay, and that's what we will do. Okay, so that's this, and the time derivative similarly will, so time derivative we already done, and the curl will simply be K times J. So overall, what we have is, if I put all this together.
So here is it psi k omega or rho k in the second step?
So
No, the second one.
this one is phi. So this whole thing, right, is phi of R omega, right?
Okay.
But now I am writing this whole equation in the Fourier space. So this is IK times phi of K omega. Does this help?
Don't you like? You're just differentiating, right?
Yeah, maybe the confusion is, okay, let's say this is equal to, this is this piece, right? So let me call that E transverse, some transverse R omega. If that's this term. This one is not the R, this is the electric field K omega. So I have made a leap here from here to here. It's like saying that you first write an equation for this, but then you want to write the equation for that. Confused. Okay, let me go through.
Can you explain it through the double T part? That part.
Here, this
No,
one,
no, in the this right hand,
this one,
the T part, double T is gonna be minus I omega.
here, this one.
Yeah.
Yeah, let me explain that. Give me a second. Okay, so let's say you have an equation d by dt f of t is equal to g of t. That's a simple equation in time space, but I want to write this in Fourier space, and what I will do is this is t by dt of the omega over 2 pi e raised to I omega t f tilde of omega is equal omega over 2 pi e raised to pi omega t that's actually minus and g tilde. Okay. Time comes in e omega over 2 pi e raised to minus I omega t and pull this both in. I have a minus I omega f tilde omega minus G tilde. Is that good? That's a true statement. If this is true, this is true. Fourier space is a complete set. These are the eigenfunctions of, these are the Fourier eigenfunctions. So this is a component of a Fourier eigenfunction. Each component has to be zero. It's like vectors. Right? Each component has to be zero. So that has to be zero. That's minus I omega f tilde omega is equal to G tilde, which is effectively what I have done is d by dt is minus I omega. That's the same thing that has happened. This is an equation which I wrote it in Fourier transform in a sense. Right? So when I don't write the left hand side, it was not okay. Because this is in R space and this is in K space. So I would equate it to something else. Okay. Okay. So I have so my magnetic field is equal to still in position and frequency, but it's written in terms of the current and the Fourier transformed space. That's equal to, I have to take a curl, right? So that's IK hat plus IK crossed with A of R omega. That's equal to I omega over C and R hat crossed with mu naught over 4 pi exponential IKR over R, and then there was J of K omega. Let me rewrite this in a certain way. Let me say minus R hat cross with. We would like to have our resistance, right? With the key multiplied by a C, and let me also multiply by C here. So C there, and I multiplied by an I, so I say this is equal to e raised to IKR over R, and then minus I omega over C. And cross with J. It's just a way of writing. So I've multiplied by a C there just so that we can get the resistance in as a unit there. This is the property of radiation. There's always exponential. This contributes only at very far distance, and this will go away on the dome, right? Because the area has that R square in it that will cancel out. Exponential part, when you square it, doesn't contribute. So this is the frequency space. Notice this is frequency, and this is wavelength, wave number, let's say. Right. So this is Fourier transformed in both time and position. And I over omega is like time derivative. Remember, it was a derivative of the current that contributed to radiation. In Fourier space, derivative shows up as frequency. So it is omega that comes in. Right? It is omega means you have to have a change. If it is static, no radiation. Static means omega equal to 0. Right? In the frequency space, static means omega equal to 0. So the moment you set omega equal to 0, no radiation. So that's the content in here. that if I get this, I completely have the radiator. In the time domain, you had to do all those integrals and to get that, here it's ready-made. Right, the moment you have the Fourier transform, you have done. And electric field, we will do it next time. It's a little more, do few more steps, but they're almost, there. Okay, so we'll do it, next time. Okay, thank you. Oh, there is a C, some of you say there is a C, there is no C, some of you say there. There's no C? Half of you say there is no C. Pravina says no C, Lakshmi says no C. That doesn't say anything. But still a bit that exists.
I have in so the here,
Long time.
percentage should be just A is going to be a vector.
This one?
Oh, the second step here, is it the vector?
It's a vector becomes the gradient, right?
Oh, okay, okay,
So the gradient acting on R, that's an R hat.
okay. So here we did like in the above equation E R omega, wouldn't there be IK outside now?
IK, yes, that's what I'm showing, yes, that's correct.
So it should be correct.
This is correct because this is phi, right?
Oh,
Here, this is rho, but this is a more explicit expression. Thank you.
We have a homework due today.
Start it again.
We have a homework due today.
Yeah, there is a homework due today, but yeah, I think what you have submitted, right? That it's the last, until now, all the homeworks it seems like.